So, well, I'll try to do it hands-on with Git. Hopefully everything will work, but well, otherwise you have the presentation and all step-by-step instructions in the conference material. So just to show you, the procedure is very similar to what we have seen already for the structural dynamics application, and it's even a bit simpler because we don't have so many options to choose from in the problem type. So we have a subset of the things that are available in the fluid dynamics application. As before, well, I'll just try to start from scratch to show you the initial setup. First thing is to choose, again, the application. First, in this case, we will use the fluid. So we select fluid and next. And we will do a simple 2D example because, well, I thought it was more appropriate for an introduction example. We will try to simulate the flow around a cylinder, which is an academic example. So we will see a bit how to go step by step, define the geometry, define the material and its properties, assign the boundary conditions to run the example, and then set up the simulation. So you already have you have in the presentation the instructions to input the geometry step by step, but it is also provided here in a directory in the course material, the fluid dynamics example. You have this fluid tutorial. Here we have the geometry already prepared. You see it's basically a 2D domain with an obstacle in the middle. What we will want to do is to have a flow coming into the domain from this side, flowing around the cylinder and exiting through the right side of the domain. And what we should see is that some vortices of von Karman vortex 3 is developed on the tail area of the cylinder. So we already have the geometry. Next step, we will define as before, the setup of the simulation, the model. So I will start from here. We only have incompressible flows at the moment in this problem type. And the approach is Eulerian. That means that the grid remains fixed even if the flow itself, the fluid particles move. We have currently 2 different solvers here available from the problem type, which are the fractional step and the monolithic. The difference between the two is that the fractional step solves separately the velocity and pressure unknowns, while the monolithic one solves the entire system, so both velocity and pressure at the same time. So in practice, what this means is the fractional step is faster, while the monolithic should be more accurate in general. Here we can choose between the two, but for this example, we'll just use the monolithic one. Sorry, the fractional step. We had already selected. Here we could choose if we wanted a turbulence model, but in this case, it's not required. Here we have, again, the options to run the problem in parallel, but we just leave the default ones for now. And we can choose the linear solver settings, but I won't go into this because, well, the defaults should work fine for most cases, but you can choose different. There are other solvers available. This, by the way, is also common to the other applications. So the solvers that you see here will be more or less available for the different problems. Then some tolerances, but the defaults are fine just for this example. And we will define the time stepping. We have here the time we want to start, 0 is fine, and in the final time I entered here 50 seconds. I want to use a time step of 0.1 second, so I just wrote it here in this little box that appears. And while I disable this, that is an initial pre-process, let's say, of the solution to improve the convergence rate, but for this example it's not really required, so I just here by default I think it performs 10 or 50 steps of this, but let's just disable it for this tutorial. Temperature we don't need to set because we won't couple it with thermal effects. So again, next step is to define the material properties. For this, I have gone to this materials tab in the right, and I already have a new material created, but in general you just have 2 of them available. And I wanted to, as this is an academic example, this is, let's say, dimensionless. So it's actually the properties do not correspond to a real fluid. We just set the density to 1 and the viscosity to 0.01, which will give us a Reynolds number of 100, which is what will characterize the behavior of the fluid. So what did I do to create this material? I went here, I pressed this new button. This creates a new material. You can rename it if you want. It should be clickable. But well, anyway, I don't have a keyboard here, so well, it should be. You should be able to rename it. And here you can set the properties, the density, and again, for the fluid, we just need to define the fluid properties. So we can go here and define the viscosity. And if we wanted, we could define choose a non-Newtonian behavior, which by default is a Bingham model. So once we have the material defined, we will go back to the Properties tab, and we click here to add a new property. I already had one, so I won't create a new one. But what you need to do is go here, select just the name, and the material you will want to use to identify a region. So here I chose the material, the fluid one, my academic material, let's say. And you just press OK. I'll cancel it because I already have it defined here. Next step would be, as in the previous example, to define the groups that we will use. So in this case, I went here and I created the different, I will close here to save a bit of space. I defined different regions on the model. So first, I need one region that will be the surface, the domain, the fluid domain itself. I called it fluid. You can see that basically what I did here is I went assign surfaces to the group that I had selected, and then I select the surfaces I want, and then I need to press escape to confirm the selection. This same procedure is repeated for the other areas. And in this case, I define the inlet, which is where the domain will come, the fluid will enter the domain. So I selected the leftmost line. I define the cylinder itself. So you go here and, well, assign the line, and you assign this, the contour of the solid obstacle. I also define the walls, the external sides of the domain, where I will apply a non-penetrability condition. So I will allow the flow to go along this direction, but not to go in and out of the domain. We will see how to do it in a moment. And I also define the outlet, so the area where I will allow the fluid to exit the domain. So once I have this defined, I go back to the menu, and I start assigning the boundary conditions. You open this tab here, boundary conditions, and you have first the inlet. Here you define the velocity. In this case, I assign a velocity in the x direction, and you decide which group you want to apply it to. So you just enter here the magnitude of the velocity and select the cylinder group, the inlet group, sorry. So I already did it, so I won't do it again, but you have here the inlet, and you can check that we assigned a velocity of 1. Here, these controls, if you want to fix, so to impose the velocity in both directions or just one. Maybe in some cases you want to impose the x velocity but leave the y free, or vice versa. For the outlet, I need to assign the pressure, a fixed pressure. This is a requirement of the fractional step algorithm that we choose. So this algorithm requires to give a set velocity in the outlet. That would not be the case in general. So the monolithic solver does not need you to define an outlet. But let's say that in this case we just fix the pressure to 0, which is will be the ambient pressure on the exit. Next step, we assign this non-penetrability condition on the walls. So we have here the e-slip condition. So we are allowing a slip. E-slip means that we won't allow the flow to go in the normal direction. It will be tangential to the line in this case. This would also work for curved surfaces, by the way. So you just need to select here e-slip and select the group you wanted to apply it to. In this case, it was the external walls. We already did it here, and so you have it on the example. Well, it's not double clicking. I'm too slow apparently to double click, but you should be able to see it. Finally, we have a no-slip condition. We fix, in this case, we want to fix the flow in both directions on this surface. So basically we are saying that we are resolving the flow up to the wall. So the wall itself will be fixed, and we will not allow the friction, tangential velocity on the walls of the cylinder. So what we will do actually is to fix the velocity in both directions to 0. We have the value here and both directions active. And again, we select it to act on the cylinder group. And well, I think I didn't mention it before, but the other thing we also need to do is to select here the element we want to use. So we want to mesh the domain using triangle elements. Well, actually there are only triangle elements, but we specified nevertheless. And we want to use this property that we defined here, which basically means that the area identified with this property will have the density and the viscosity that we decided before. So we actually go here and say that on the fluid, so on the surface, we will mesh with triangles and using the property, the material we defined before. Fluid elements are all linear.
Only linear?
Yes.
Can you show that?
Yes. I mean, in the case of the structure here, if you want higher order elements, you could check it here in quadratic type. So you could choose to use higher order elements. These are, I think, 8-noded hexahedra, and these are 8-noded rectangles and 9-noded rectangles. Is that right?
In triangles we have normal and quadratic. In quadrilaterals we have normal, quadratic, and quadratic 9. And in the triangle we have normal and quadratic.
Okay.
So yes, we have three ones that we can select. We have more than that, but from here we can only select this type of quadratic element. Right. Thank you.
So again, the finally, this is the same as we already saw for the structure. So we are using a delta time of 0.1. Here we say that we want to print results every 5 steps, so 0.5 seconds. And on the nodes, we will print the velocities and the pressures and the reactions. These are the same output options for the file that will be produced from Kratos, and then we will read in the post-process. And in the case of the fluid, we were interested in seeing the reactions on this, the resultant force acting on the surface of the cylinder. So what we actually did is to select this drag calculation option, which will basically calculate the reactions on the selected entities and print them to a file. And we went here and we said that we wanted to calculate the total force acting on the cylinder group and print it to this is a text file that later you will be able to import to Excel, for example, or any kind of graphing program that allows it. So with this, we have everything we need. We just need to mesh. Well, we already have a mesh, but I'll just do it again to show you. And in this case, I selected 0.9 to thanks. We just enter the size, and the mesh is fast because there are not so many elements. No, it was 0.2 actually, right? So this one is coarser than the one that you have in. So yeah, 0.2 again. Sorry. You have the mesh, and well, yeah, I think this is the one that you have on the example if you want to use it from the folder. Once we mesh, remember to save the model. Git will tell you to anyway, but before calculating, we always need to save the model. And then once you have it, you just calculate. And, well, it will just tell you a warning, but yeah, we are not assigning initial conditions, but they are not necessary. I mean, they are helpful, but in this case, we don't need them. You can see the process of the calculation here in this window. This is also available here. And here, well, basically this, in case everything works, that is not so useful, but when there is a failure, you will get an error message, and you can check the output to see what went wrong. And then you can also switch to the post-process. Now it's giving me a warning because it's an incomplete file. It will be complete once the solution is finished. And here we could, for example, display, I don't know, the pressures, for example. We can see that vortices are forming on the back of the cylinder. We could animate the solution. Well, you already saw this, I guess, in the Git part of the conference, but you can visualize the different results that you have from your calculation. Yeah, okay, so it eventually finished. And now, well, we could open the complete file. Should be in the, no. Well, we just switch back and forth, and we have the file loaded again. But well, basically it's the same thing you could see before. And then we could check maybe on this folder. I'll just, if you open on the results folder, you can go back to your model, and you could see this reactions file that I mentioned before. Did I run it from here, actually? Yes. So, well, that's just to show you, but it has printed here at every time step the X and Y components of the forces acting on the cylinder, which, well, is the kind of thing that we sometimes want to check in flow problems. And well, this is what I wanted to show you for the tutorial. I'm open to questions if anyone wants to ask, and well, I guess we will see around, each other around in the coffee break if anyone has questions. And well.
Ok, da igual. Sí. Okay. Okay. Bueno, we had persistence. Hello, everyone. I'm Miquel Santasusana. I'm going to explain you what we can do with discrete element method in Kratos. And meanwhile, I introduce myself. I put this presentation just to show that here we simulate. Well, discrete element method is an application to simulate particles, and this is just an academic example. And what you see here, these colors, is different partitions because this was calculated using MPI. And each color corresponds to a different processor. So we make use of all these capabilities that we have in Kratos. So I programmed the discrete element method, for example, and then I could make use of MPI capacities of Kratos to couple it, to use it in this application. Okay, these videos, you have seen it already. If you can click on it. You have seen some of these videos before in Antonio's presentation. I just wanted to tell you that discrete element method is one of a good example of application that can be coupled with others. In this case, we are just simulating particles here. These are rigid walls, so no finite elements are being calculated here. This is another example where there is only particles as a matter of interest. But this is also just particles, and in this case, what we are calculating is not granular material, but this is supposed to reproduce a continuum model. And here, can you do it again? Okay, this is a uniaxial compression test. So you can see that typical failure of a concrete specimen. So we can deal with particles with different approaches. Well, this is just another video where we can see a BTS, a Brazilian tensile strength test. This is the 3D complete model, and this is just a CAD where you can see better how the displacement and how the fracture evolves. Okay, so these are just DEM applications, but we can also couple, since we are in Kratos and everyone speaks the same language, so I can couple the application of them with the application that Josep Maria has introduced to you before, that it was solid mechanics application. And it's nice because you will see it after the break. When you get into Kratos and you want to be a developer or advanced user, you can code and you can combine different strategies. And in this case, there is a solver that solves for the particles, communicates the forces with the structural application, and then there is a solver that solves for this structure. Okay, and I can use all the elements that are available in the solid mechanics application. So this can be small displacement elements, large displacement. I haven't coded it. I just dealt with the particles, but then I just call one solver and one application and the other one. Okay, and another good example is related to the tutorial that I'm going to show you right now, is to couple them with a fluid dynamics application, and it's the application that you have seen from Jordi. Okay, so here we have fluid and particles inside, and again, the application that Jordi has coded solved the fluid, while the other application solved for the particles. And there is some interaction, so you have to code something, but it's easier because everything was in Kratos. So it's not only C++, but it's also the same framework, okay? Okay, so now I will go through the problem type that is available, because I want to emphasize that you have to distinguish in what is Kratos and what Kratos can do, and what we have in a problem type of Kratos available for any user. So by just following these easy steps, you can generate specific cases. So in this case, we are going to be able to do some example that has DEM particles and fluid. But you have seen many of these applications. But so once you have, you can do anything in Kratos, but you have to work more if you want an user interface that has to be robust and has to be, there cannot be all the available options. For that, you have to be a developer or advanced user of Kratos. Okay, so that was all, and then I will go through Git and try to use this problem type. You can, okay. In the pen drive, I think you have one example and also a tutorial of this problem type. So again, I will get back to post-process, pre-process. Dígame. Ajá, vale. This one, okay. Okay, so I'd rather be there if I have to use a keyboard. You have this example in your folder, so it's just an example that everything is defined already. So here we have the geometry, which is a pipe, and has an inclusion, has another pipe inside. There will be fluid flowing from one side to the other, and there will be an inlet of particles. This is one of the new features we have. And well, I've defined the groups, so we can see where will be the inlet defined. This is where the DEM particles will enter, and we have another inlet, which is where the fluid will enter the cylinder. So it's not the same entity. We can print both of them. So you can see, well, there are two different surfaces defined. We have the fluid domain, and then conditions that Jordi has talked about. These conditions. This is a non-slip condition. These are the walls, and okay, there is the end where we have to define a pressure boundary condition. So again, I will go this quickly because you already know most of this. This is again the fluid settings that Jordi has explained it to you. So you define again the same settings as before. You have to select which element are you using. In this case, it was tetrahedra because it's a 3D mesh. That maybe we can see the mesh. Okay, I can. Here I can switch from the geometry to the mesh, and here we see. Well, it's not clear, but if you zoom in, you will see that these are tetrahedra. And I try to go back. Okay. So where else? Well, the initial conditions. In this case, yeah, there is initial velocity in this fluid because I want the conversions to be faster. So I set some values for the initial velocity. All the fluid is going to start moving in z direction with 1 meter per second. And what else I need? Then the boundary conditions, which is an inlet velocity. So there will be flow entering this pipe. I can see again. This is very convenient because if you want to introduce just a condition, it's better to prepare before the groups and then just assign the groups that you selected before. And also, if you remesh, the group is updated, so the conditions are applied to the new mesh. Okay, and finally the pressure on the other side, and that is okay. And then the non-slip condition would be the walls of the model. Okay, so this is the fluid that you already know more or less how it works, and then we have here the settings for the discrete elements. And what we're going to do, well, you have many options you can explore later on. And also, I haven't said this, but well, on the coffee break, you can ask me anything you want. And if you try it at home, you can send us any emails if you find some mistakes or if you want to know anything. We are open to answer questions because we want the community to grow. So don't hesitate in contacting us. So we see there is a bounding box because some particles, the particles flow and go away. If we want to limit our domain of calculation, we can set a bounding box where we can eliminate the particles outside this bounding box. Gravity, in this case, well, we are using gravity, but it's not important because the velocity of the fluid